It has been over 100 years since humans first took flight. Since then, we have built airplanes, rockets, helicopters, all letting us travel fast and far. But making something small, efficient, and maneuverable has been out of our grasp. However, new discoveries about the way animals move are making it possible to construct machines that could revolutionize the future of robotics. At UVA, researchers are taking a closer look at dragonflies to discover how they work and how that knowledge can be applied to make the next generation of robots.
Why do humans study nature, and why has nature created better machines than humans? My name is Ayodeji Bodioke, and I'm a graduate student in mechanical and aerospace engineering. I'm from Nigeria, and in Nigeria, malaria is a big problem. So since when I was a child, I've been killing mosquitoes and all that. But I actually never thought that. It's weird because I've seen airplanes fly, helicopters fly, but I never thought that insects were flying based on similar principles until I actually started working in Professor Dong's lab.
Human has a long history of looking at something happening in nature and trying to design something similar. Flying vehicle definitely is one of the example. My name is Haibo Dong. I'm an associate professor of the Mechanical and Aerospace Engineering Department at UVA. And my work is primarily working on the bio-inspired flow and trying to understand the flow physics.
Well, we can think about aerodynamics as split into two. There is steady, and then there is unsteady aerodynamics. So when we think about steady aerodynamics, we're thinking about aeroplanes. So if I'm flying and I take my camera and I'm taking a picture of the wing at every time, it's gonna look the same. Whereas in the case of insects, which is unsteady aerodynamics, things are changing with time. So every time I take a picture of the insect wing, I find something different because the wing is moving back and forth.
This kind of unsteady motion and unsteady fluid dynamics actually also offer them lots of abilities. And for instance, their size is very small. And any kind of wind to us is maybe a small wind, but to them is more like a hurricane or tornado. But with the unsteady, motion of the wing, they can easily adjust their flying, stability and trying to maintain the flight.
Insects flap their wings back and forth. They actually generate a tornado on the wing surface. What is a tornado? From your daily experience, when a tornado occurs, it sucks stuff in. So if I have an extra low pressure on top of my wing surface, then that can help the wing generate more force. The beauty of engineering is that when we are able to study nature, understand the secrets, and when we build these robots, then we can actually surpass what nature can do. So how do you study an insect? Well, it's simple. We just go outside, we go to a pond. You need to have your nets, of course, in order for you to catch the insects. And once you catch them, you put them in a cage, and then you bring it to the lab. Do you guys want to see? All right, so we're at the dell. This is where we catch the dragonflies. Let me kind of survey the area first to see if there are any flying around. Where there's grass, where there's water, the chances of finding them there are higher. So that's why we always come here, because this is like the only source of water on campus. This is strange. I haven't actually spotted any dragonfly. I don't know how to swim, so if I fall inside, someone should rescue me. Is that a dragonfly? Yeah, it's moving so fast. I can't. It's more likely a hornet. I don't think it's a dragonfly. Oh, that's a damsel fly. So damsel flies have very flexible tails. They can actually curl it back. Don't forget, the world is very big to the damsel fly, so it can't really see you doing this. So we can ask Will if he found anything. I think we might have a higher chance of finding the insects closer to that side where this twigs in the water, because they tend to hang around those areas. It's like so nice out. I don't understand why the dragonflies are not out. Yeah, they knew I was gonna come catch them and take them out of their natural habitat.
I gotta go.
Yeah, I don't see anything here. Do you have the box with you?
Oh, no, I can go get it though really quick.
Okay. Okay, I got a bumblebee. Okay. Yeah. I got the bumblebee. I've got it trapped in there, so it's not going anywhere. We didn't get dragonflies, but bumblebees will do. So when I let it go, you just close it.
Okay.
All right. Okay, close. Don't worry, no insects were killed during this process. We'll release the bumblebee back when we're done. So we just finished catching the insect, the bumblebee, in there. And so we're gonna take it to the lab and do some filming of the bumblebee. Go ahead. So we're on the first floor of the Mechanical and Aerospace Engineering building. So we're going to go into 104. All right. Hi, Joe. So we're just gonna run through the process of how we film the dragonflies.
Oh, okay.
Yes.
Okay.
Yes.
So,
Yeah, we got a bumblebee.
Yeah, bumblebee today.
oh.
So yes. So here's the setup that we have, and that is the tank. So it's all glass now. Like I was telling you before, we used to have it open, but then the bumblebees were flying everywhere and people got scared. So we had to make a glass tank. And so we have, you can see there are cameras rigged everywhere. These cameras are shooting at 1,000 frames per second. So dragonflies 25 times a second. These cameras are perfect for handling that kind of motion. Each video is between 0.15 seconds to like 300 milliseconds. And for the dragonfly, that's a lot. That's a lot of time. All we just need to do then is to remove the bumblebee and then just lower it in. Oh, one more thing. In order for us to track the motion of the bumblebee or the dragonfly, we need to dot the wings. We cool them down so that they are not flying around and disturbing everyone. Because once you cool them down, their muscles don't fire as much anymore. So we take a marker and just dot the wings, 3 dots in the chordwise direction. So when it's time for us to reconstruct, that will help us know the orientation of the surfaces and things like that. It's so chill. So the bumblebee, is excited to be in a cold lab, so it's not really moving. So I'm gonna reach into the cage with the net in my hand, and that's what I'll use to grab the bumblebee. Okay, so, man, this buzzing sound is so loud. Okay, so now I have the bumblebee. I'm just gonna take it into the shooting area. I'm gonna just lower it to fly around in there. So we turn on the lamps, and the lamps heat up the body of the insect. And once they're warm again, their muscles can fire. And then we have an automatic trigger system. So immediately they take off, it triggers, camera captures the motion, and bam, I'm done. I have my data. From that, I can construct a dynamic 3D model. So for every picture, I have a 3D model. When I play back, it looks like the insect is actually moving like a video. And this is what the reconstruction process looks like. So we have an image, and then we create a template based on the image, which is this thing you're seeing in blue. And then we manipulate that to match the images at each different frames. We're able to match it very accurately. And so when we play everything back, we can get all the motions, the back and forth motion. Then I need to simulate the interaction of the insect with the air. The way I do that is I use a computer software that we wrote in this lab. And after I'm done, I'll come back 4 days later or a week later and check my results. I can post-process my results in terms of what a human being can understand. You can see that at the leading edge of the wing, you can see that a bubble is beginning to form. So that's the low pressure region. That is the leading edge vortex. The tornado I was talking about. If I take a slice cut on it, like if I take cross-sectional cuts on this, you can actually see things spinning around inside. The beauty of this is that it can show me things that I wouldn't have known exist. just by observing the flight video. It gives me an insight into how the wings are producing forces, which is very important for engineers. Okay, so I'm done with this bumblebee, and I'm gonna just go put him outside. As I promised, no insects were harmed. Okay. So back into Mother Nature.
So part of the trick of fundamental research always is making it apply to a real engineering scenario.
We want to learn from nature and borrow it, for the current design.
We are looking to nature for inspiration, and after getting the inspiration by mimicking nature, we hope to be able to surpass the solutions that nature has come up with.
The most important next step is trying to see how much of those findings from the nature locomotion and can be implemented into the next generation of robot design.
One of the big draws for me coming to UVA was that as someone who's interested in fundamental fluid dynamics, I would get to work with people who are developing finalized autonomous vehicle platforms. We'd study a piece of the vehicle, maybe in a controlled setting like in a water channel. We'd study the flow coming off that piece of the robot. And then, since we're in this very repeatable setting, we can run experiments. We can look at the flow when the fin does one maneuver. We can try slightly different kinematics. We can change the stiffness property of the fin. We can really tune the fin in a systematic, repeatable way. And because we're doing experiments on actual pieces of a finalized robot, then we can try to implement those pieces back on the robot. And sometimes the fundamental scaling laws we come up with will work really well. Sometimes they won't work really well, and we'll have to go back to the water channel. And it's this iterative process for completing a truly autonomous vehicle. One advantage of this is cost. A lot of the traditional underwater vehicles we have are very expensive. If you have simple parts, just like if you have one fin that's both a propulsor and a maneuvering device, like it is for many fish, you can scale this down to something much more cheap. For a few $100s, maybe you can build a small autonomous vehicle. And what that means is you can let out whole fleets of these. You could send out 100 robotic fish to take temperature measurements for climate science, to explore a coral reef for diagnostics if you're studying the ecology of an underwater system. So whether you're underwater or in the air, having something small, quiet, and cheap opens up tons of possibilities for applications.
Every day I go to the lab, I learn something. I learn something new.
We don't think anything we do is just like almost the end of this research. No, it's actually the start of this kind of research. So we need more and more students and also the faculty to join this kind of team.
There are a lot of fields where you're just looking into the structure of the universe and maybe there's no application. And there's other fields where you're definitely building something cool, but you may not be improving our fundamental understanding of the science. And bio-inspired engineering has both. We get to work with marine biologists. We get to study how evolution guided the structure of fish and why the earth is built the way it is. But at the same time, we're designing vehicles that can really impact actual human lives.
Going from knowing nothing to actually knowing something and actually contributing to the knowledge of other people. I think that's the most exciting part about research. Like, data collection is nice. Like, I like to get the insects. I like to film them. I like to, do the analysis. But if you want to see your growth, just compare when you started doing the research and you not know anything to like where you are now. And I think that journey for me is the most exciting.
It's important to discover the science and something, but it's also can really make the students excited about the research and be devoted to this career. I think that's definitely something I really feel very proud of.
Because there are so many smart people and people have different perspectives. So after engaging in conversation with them and you working on your craft, you can then start growing. And the growth process for me is just the best.